It's my pleasure to be present. I'm Mikhail Mikhasenko, a professor in Ruhr University Bochum, and my task today is to bring the crowd into the domain of the physical sheets, introduce analytic continuations and basics of the complex analysis. I will structure my lectures in 5 parts. I will start with the introduction of the complex functions, then we will discuss branch points and poles. We'll move into discussion of the Riemann sheets, and then move finally to the scattering amplitudes and discuss their properties in the complex plane. I'm going to share my notes and write by hand, and welcome to all questions that come up. Feel free to spot typos and help me to proceed. I will be held by a little fox on the side of the screen, and start with analytic functions first. So it tells me that, hey, I'm smooth, drama-free, and don't blow up. I must be analytic. Yes, you are. In fact, this captures the essence of the analytic functions that we will go into. But let's start with the complex one, with the complex variables. Complex numbers extend the domain of the real numbers by keeping track of the imaginary part. And both in the real and imaginary part of the numbers are arbitrary numbers from the real axis, such that any complex number can be moved into the dimensional domain. And we will be using this representation a lot, where on x-axis I will be plotting the real part of the number, on the y-axis I will be plotting imaginary part of the number. So that's not really a plot, but it's rather domain in where my variable lives. So for any number in this domain, one finds the real and imaginary part by corresponding axis. And for the convenience often, instead of writing the axis labels, I will be just labeling the plane itself by top corner label z. So this is our z-plane, where location tells us what is the real and imaginary part of this variable. And when we talk about complex function, we are talking about any function on z. So the function prescribes the operation that we have to do, and there are millions of examples. Let's say z square is the complex function, or log z is the complex function, square root of z. Essentially, whatever you want, you can think of is everything is a complex function. Important point that was stressing is that computer programs introduce algorithm that operates with the complex functions, and essentially this introduces a function. So the computer programs play with the complex variables, and the certain set of operations introduces how the variable transforms, and that introduces functions. So I'm not restricting myself to, let's say, things that can be written analytically on the closed form, but any algorithmic procedure would also introduce a function. And once it operates with a complex variable, it will be a complex function. Analyticity is a stronger condition to a function. The analytic function is introduced by the fact, or the function is analytic where there is the convergent power series. Could be infinite. The power series, once it exists, the function is analytic. However, this is sort of mathematical definition, and I that's not checking this condition is not what we do when we state the function is analytic or not. What we rather do in most of the cases, we identify the places where a function is not analytic. And in the rest of the domain, one of the definition in the complex z-plane, the function remains analytic. You can hear sometimes when you talk to mathematicians or when you read Wikipedia that sometimes analytic functions are also called by more fancy word holomorphic. However, in the context that we'll be discussing today, these are synonyms. What is cool about analytic function, and one cannot understate that, is that integral over closed contour for the analytic function is actually 0. In my z-plane, I can choose the contour, and as soon as the function is analytic in the whole domain, the integral is going to give me 0. It's not just a mathematical statement, something that you see practically in the following way. This integral can be written in a sort of finite form where you would sum over points, you split the well, in that case, let's say this circle, we parameterize the contour by circle, say this is integral of f of z naught plus I and then in the finite form, it's going to be equal to and my image is dropping, isn't it? But
yeah, sometimes it switches off, but it's back. It's okay.
In fact, any analytic function would give me 0 once I sum along the circles, keeping the phase. Take any function, take a square root of z as the f of z. At, let's say, z equals to 1 plus 1, and then r is equal to 0.1. Or take any other function, and analyticity tells you that the integral must vanish, and it does. Interesting properties of the analytic function show up when this function is not purely analytic within the integration range, but rather contains singularities. Well, coming back to the end of this section and saying that analytic function indeed is something that is smooth, singularity-free, drama-free, and don't blow up. There are no infinities. You can think of the domain of analyticity as the function given by high-order polynomial. And these are analytic functions. Let's discuss what are effects of a non-analyticity one sees within the functions. And now I'm moving to the section to discuss, next section to discuss branch point and cuts. And in this section, we will see how does branch points arrive either from the algorithm of the computation or from definition of the fields where the function is cannot provide an ambiguous answer. So here we are. We are the second sections related to the branch points and cuts. And I wanted to start with the basic function that we use all the time, and this is a square root function. And the first thing to realize that this function is not analytic everywhere. And we will see this if we compute the function in the z domain at 4 points. 1 plus I epsilon, 1 and minus 1. Square root of 1 is 1, and it doesn't matter what you add, I plus epsilon or minus epsilon. But once we compute it on the other side, the answer is going to differ depending from which side on the real axis you compute this. From minus epsilon, the answer is minus I. And on the other side, it's a plus I. You can right away open the Python terminal and ask for minus y minus 0.001j. So that would be small epsilon that you add, and you will see that it's not the same as the. And in fact, this is not specific to any particular implementation. So all of the programming languages and all of the frameworks, they use the same definition of the location where the function has a discontinuity. What we have observed that, in fact, for all negative values approaching, so value of the function computed from the top and from the bottom are different. And this manifests itself into, or that's what we, in the domain of analytic function, we say that from that direction, you have a different value from that there is a discontinuity, and we indicate this by the branch point. So sorry, by the cut. So what we are going to draw now is the heavy wavy line that tells us that there is a discontinuity. Approaching from top is not the same as approaching from the bottom. There is a sort of border that analyticity cannot cross. So now contours cannot be drawn. The contours can be drawn everywhere, but if you draw the contour like this, the integral of a contour will still be 0. However, as soon as you cross with the contour, the branch point, your integral will vanish. So the line is simply indication for us that there is a discontinuity. And the line itself is called branch cuts. So the line. So this is the branch cut. And then the heavy point is a branch point. Every cut has to start somewhere and end somewhere. So the cut is really connects to points. And in that case of the square root function, one of the branch point is sitting at 0. That's where our discontinuity starts, and it ends at infinity. And let me give you some illustration examples. For standard function, we can easily figure out where the branch cuts lie. For example, square root of z minus 3 will have a following analytic structure. The branch cut is at 3, and then the branch point is at 3, and the cut goes from minus infinity to 3. The function square root of z minus 3, z minus 5 has 2 branch points, one at 3, another one at 5, and then there are 2 cuts that and there is a place where there are 2 cuts to cross. Then another interesting example is the product. Fetch function will have an analytic structure that with the cut connecting 3 and 5. And to surprise you a little bit, maybe for those who haven't seen, if you plot function where you connect two multipliers into a single expression and put it under square root, you will see that analytic structure in that case is somewhat different to the previous one. So the cut is not connecting two points, but it has this shape. And that happens from the, so essentially one needs to see where the argument of the square root of the expression under the square root crosses pi or minus pi, and that's what determines numerically where the cut is located. All right. Let's see if we covered everything here. The branch cuts are covered, maybe worth mentioning poles. Poles are isolated singularities in the complex plane. There might be dots where, again, the Cauchy theorem will not vanish, and those are the poles. And the example of this, f of z is equal to 1 over z minus 1 plus I, and that 1 plus I. So the function, it has a pole at 1 plus I, as you see here, and there is a pole in the z-plane. The Cauchy integral for this function around the point 1 plus I is going to give us 2 pi I, and this is the integral Cauchy theorem. Another interesting observation that the poles are places where amplitude blows up, and if one would look at the function along this line, starting from 0 and going to 1, if I am plotting, let me plot in my variable t that starts at 0 and goes to 1, my function f3 of z, absolute value of it. So while we pass by poles, the function is going to show us that, I mean, the function is strictly infinity at the poles, but in vicinity of the poles, they influence the value of the function. So what happens, what you're going to see is that there are peaking structures related to the fact that you pass by the poles. In absolute value of the amplitude, there are a reflection of this. One of the analogy that I have in mind is that these points, the poles in the complex plane, they are sort of sources of a signal, and then depending how close you are to the source, you experience influence of that. Let's move further. So and let me introduce the Riemann sheets. Let's say our function f, well, what we've seen before, that any complex function is defined in the complex plane up to singularities. So there is this complex plane that we considered, and except a few singularities, the function is defined. And let me call f1 of the original function. We can approach the function and see that there is a discontinuity, obviously, along the cut. And the figure that I draw here corresponds to a function with the branch point at 0 and a pole at 1. So example for this function would be, it's a square root of the, let's say, plus 1 over z minus 1. What if I come up, if I tell you that I come up with another function, f of z, f2 of z, that's also defined on the z plane. So here is the f1 and here is f2, different function, but it has exactly the same values as my original function below the cut. So I approach the cut for the top function from the top, and I'm finding for the other function, I get exactly the same values below the cut. Moreover, the function is analytic if I just merge the two. So let's say this is our z axis, so real z, and this is our cut. And if I plot f1 and I have f2 here, I can draw circles, I can integrate over them, and integral will vanish. So the function is actually analytic on this domain. Then they say f2 gives an analytic continuation of f1, and f2 is analytically connected to f1 and gives analytic continuations through the cut. So the first picture is called sheet 1, and the second picture would correspond to the sheet 2. They say that this is actually sheets of the same function, of the original function f. Sheet 1 is where you don't need to do anything, so you just compute the value everywhere on the z, and this gives you a whole complex plane covered with the values where you evaluate your function everywhere. But then, yet this function has another sheet that is analytically continuous through the cut. And that's all it has in it. One can come up with, well, many function has multiple sheets, meaning that there are a set of functions that are related to each other through the domains of analyticity. And I am going to continue with my examples and show you how they are connected. So let's start with the square root of z. On the right side, I will be showing how f1 looks like, and on the left side and on the right side, I'm showing you how f2 looks like. So we want to some function that analytically continues the original one from the top of the cut, and in fact, f2 in that case is just a minus z, and one can convince themselves in this fact by plotting and seeing that there is the transition is smooth from the first sheet to the second sheet. We agreed that, or I show you that z minus 3 times z minus 5 had an analytic structure with the cut connecting 2 points from 3 to 5. And then the function on the second sheet will have the same analytic structure, and in fact it's minus. So we come on this side under the cut, and we appear on the second sheet. Another example we looked at is z minus 3 plus z minus 5, and analytic structure in that case was this. So if you come here, you're going to end up on the second sheet. It has the same analytic structure with the cut here, cut there. And the function is square root of z minus 3 minus z minus 5 under square root. But we see that there are more, actually, one can do, for example, one can try to go and see if there are functions that can analytically continue the values that one finds here. So I'm going to enter here, and in fact there is another function. Here's 3, here's 5. That would match these errors, and the function is z minus 3 with minus sign minus z minus 5. In that case, we have to deal not with the 2 sheets, but with more sheets, and there are 4 different possibilities for the signs. Therefore, this function has 4 sheets. The one that I didn't describe is that when we only cross the cut related to the 3, so sort of when you go in that direction. Important to take is that Riemann sheets are numerically correspond to different functions. And what this language of you calling Riemann sheets the sheets of the original functions might be suggesting different, but I prefer to think of this f1, f2, f3, and f4 and f4 as the 4 different functions that have some lines along which they continue each other. All right. So what's with our expression for the T matrix or for the K matrix? And the singularities of our T are coming from 2 places, from K and from rho. Expression for the rho reads as the product of the 2 square root points S minus the sum times S minus the difference divided by S. So if you plot analytic structure of rho in the S plane,
we will find that there are two, we see already from this expression that there is the branch point at m1 plus m2 squared and m1 minus m2. And the branch cut connects the two. One also finds that s equals 0 is a singularity and it's a pole. What's for k? If we restrict ourselves to the pole contribution, the k has poles at real values. And while the branch points of the row remain the branch point of the T, the poles that one puts into the K, they are not any longer the poles of the T. So the T equals to 1 minus I rho R. So in fact, what one finds the analytic structure of the T implemented in a way that we prescribed here is that it has a bunch of branch points. So this is MA1 minus MB1 squared. And there might be more if it's couple channel. For the channel 2, and they share, and there are a bunch of poles in the complex plane. When computing the amplitude, one always have to be careful when evaluating the function and on the real axis, because in that implementation, one always one has the cuts along the real axis and the values from above, one matching the value from below. But it's damn clear how to analytically continue that since we deal with the square root branch points. For the square root branch points, the way to change its the sheet of the function is to put a minus sign in front. So essentially, for all of the branch cuts, the other element sheets are hidden for the function that will provide us the other element sheets will have a different sign in front of the row in the K matrix construction. So here is the row is the diagonal matrix. It has a row 1, row n in the space of the channels, and the other sheets will have different sign for the row. Instead of plus, you put a minus. So once again, the entire byte space here in my sketch is a domain of analyticity. Function is analytic, and any closed contour integral will give me 0. Only the poles are structures that make my structure my amplitude interesting, and they are producing the large distractions along the real axis. Everything that one sees in the data, when you look at your scattering amplitude along the real axis, are given, and is a manifestation of the singularities in the complex plane. Once it's a bump, it's likely a pole in the complex plane, and narrow structures like cusps are produced by the branch points. You see that the black dots here are the branch points, and that's where the function is not it's smooth, but the derivative is broken, so it has a cusp. Well, let's now look at the realistic amplitudes and what are complications and what is analytic structure for the realistic amplitude. And one thing to realize that, well, from the previous section, sorry for coming back, we already have an algorithm to find the poles. You look at your T matrix, you implement this numerically, and you have to make sure that you can call this function for the complex Z. So one has to use implementation in your language of choice, such that it's happy to compute the value of the rho and k when S becomes complex. And for most of the programming languages, it's not a problem. And then you have to be reasonable of computing function away from the singularities, putting I epsilon to right places, but analytic structure is rather straightforward. There are branch cuts that connect threshold and pseudo threshold. And then one can explore, actually plot a function in the entire Z plane and find the poles. That's it. One often finds discussion about discontinuities because of the slightly more advanced construction. Let me remind you where I rho comes from. It comes from the propagation of two particles taking on mass shell. So what we computed is the I imaginary part of real bubble diagram in field theory. And well, factor 16 pi perhaps. But instead of the rho, one can take the proper bubble diagram and look at the, let me just write it. So the sigma of S is another function you see sometimes in the construction. And this is literally, let's say 16 pi times integral dka m a minus squared minus ka d4. It's a 4-dimensional integral. Bubble diagram, two propagators. Here I have a Ka, this is mass A, and here I have a P minus Ka, and then P squared gives me S. And one can ask a question, what is the analytic structure of this sigma term? Well, this function, let me say is called often Mandelstam, and it's analytically computed. It has a closed form with logarithm. It's called Mandelstam function. And imaginary part. Of sigma is equal to rho. So the K-matrix construction that we discussed so far and what Ilya has implemented had this had only rho, but you often see, and also in the following presentation from Lena, that instead of, so the T, let's say advanced, instead of using rho, you can use sigma. Advanced is 1 minus K sigma minus 1. Okay. And analytic structure of my sigma is interesting. So it actually has a different, despite that it matches, imaginary part of it matches rho, it has a different analytic structure in my S plane. It doesn't have the second branch point. It starts from MA plus MB and has a cut towards the right. And in fact, that's the analytic structure of the scattering amplitude. And the construction, which we call advanced here, is the one that is forced by unitarity. And field theory suggests us to use, that we're supposed to have in scattering theory. I mean, according to unitarity prescription, you have a cut. The amplitude is real below the cut and starts gaining imaginary part once the cut starts. And T that analytically continuous. Let me maybe first put sigma of S is the sigma first S minus 2 IO. My amplitude, field theoretical amplitude, the one given by the loop diagram, can be computed anywhere in the complex plane, and in fact, it's analytic everywhere except branch point and branch cut starting from the threshold. And then I can come up with the sigma 2, which has very similar structure, and it continues analytically, such that if I merge the two, I will have a domain analyticity. Therefore, I introduce the T1 of S is a regular amplitude in complex. And in complex S, regular, I mean, is the one we introduced before, is the 1 minus K sigma minus 1 K, and then T2 that would continue would be introduced as the 1 minus K sigma 2 minus 1 K. And finally, that's expression that naturally comes from analytic properties of this loop integral. And Mandelstam function needs to be analytic continued by adding the discontinuity across the cut given by the rho. Last expression is how to characterize resonances. So the T2 of S in the advanced construction is going to have a singularities in the complex plane, which are the poles correspond to the resonances. So there is 2 points, and what I'm going to determine is their position. And from the position of the resonance, the position of the resonance is characterized by the mass and width, the real and imaginary part of the square root of the position. And these are called pole parameters for the resonance. Every resonance corresponds to a pole in the complex plane, and proper characterizations of the resonance that do not depend on the parameter, do not depend on the particular production mechanism, but really characterize the properties are the pole parameters. One can also find the pole. One can also find the pole coupling, pole residue, if in vicinity of the point expands the amplitude as the G squared S minus S pole. And then G squared is computed as the minus 1 over 2 pi I integral over this around this pole of my function T2 of Z dz. So that's called residue. In the pole. And it shows how much the particular how much the pole is coupled to particular channel. In case T is a matrix, the residue is also a matrix that one computes. Rj is equal to 1 minus 1 over 2 pi I integral Tij. And this matrix factorizes, which comes from unitarity. The proof of this factorization is non-trivial, but given in a few books, for example, in Gribov, a strong interaction. Well, it's moment where I would like to hand over to our chairman,
and finish the lecture.